Okay, some ideal gas law practice questions. Question 1. A student carries out a chemical reaction that produces 0.024 moles of hydrogen gas. What would the volume of hydrogen gas be at STP conditions? So let's solve for volume from the ideal gas equation. This is the relevant information in the data booklet. You're given PV equals nRT. That's the ideal gas law. And then you can rearrange it that volume equals nRT over P. So N is moles, T is temperature in Kelvin, P is pressure, and R is the gas constant. Gas constant is given here in the data booklet. So now we're just plugging in. This says STP conditions. STP conditions is also given in the data booklet. Stands for standard temperature and pressure. So that's 273 Kelvin for the temperature and 100 kilopascals for the pressure. So we're just plugging in. We've got 0.0240 moles. Our gas constant is 8.31. Temperature is 273 Kelvin. And pressure is 100 kPa. Now the rule of thumb is that if we use kPa for pressure, the volume unit that we're going to get out is decimeters cubed. Those two go together. The SI units of pressure and volume are Pascal and meter cubed, and a kilopascal is 1,000 times bigger than a Pascal, and a dm cubed is 1,000 times smaller than a meter cubed, so the two changes cancel each other out, and so these two units are the ones that we will usually use. So if we plug all those values in, we get a V out of 0.544, so that we need to know that that's in dm cubed, and so in centimeters cubed, 544 cm cubed. Now the question didn't ask for it in cm cubed, but oftentimes they ask for a volume in centimeters cubed, and so you should be prepared to do that conversion very quickly. So this is the answer to the first one, this many moles of gas, and it doesn't really matter that the question says hydrogen gas, because all gases, the same number of moles will take up the same volume. So don't worry too much about which gas they talk about. Now the next question says, what volume would the hydrogen gas be at SATP conditions? SATP are also given in the data booklet. It stands for standard ambient temperature and pressure. So you can see all that changes is the temperature. It's a little bit warmer, 298 instead of 273. So we would expect that the gas should take up a little bit more space because the temperature has increased. That means the volume will increase. So we plug in again, and we get the same moles as in the first question, the same gas constant, the 298 Kelvin instead of the 273, and 100 as the pressure. And you plug it into your calculator, and you get out 0.594. So 594 centimeters cubed. Okay. Next, if you're doing an experiment to collect gas and determine its molar mass, you probably end up with an experiment that looks something like this. You've got your container of gas, and you can release gas. These bubbles represent gas bubbles that are being collected inside of an inverted cylinder. And this is water. So you're doing this in water, and the cylinder starts out being full of water also. And so the gas will bubble up and it will push the water out. And so then here you end up with your volume of gas. So you can measure it with the cylinder markings, so you know exactly the volume of gas that you'll have. Okay. Now we can determine molar mass of a gas. We can rearrange the equation directly. We know it's mass and moles, and we can replace moles in the ideal gas law equation because it's PV equals nRT. So N equals PV over RT. So you could do this right away and have PV over RT instead of N, and then you could make that a little neater by saying MRT over PV. So this equation here actually equals the molar mass of the gas. So we could just go ahead and solve it in one step, but the IB question may break it down for you into individual steps like this question does here. So first you're going to find moles, which is what's on the bottom here of the equation, and then we'll do the mass divided by the moles. So for a gas, we'll get the moles like we just solved for. N is PV over RT. Okay, so the pressure I have here, that's 101.2. I always want to use kPa. When I use volume, I want to make sure that I use decimeters cubed. kPa goes with decimeters cubed. So I've converted that one quickly to decimeters cubed. I've got R, 8.31, and temperature here is 23 Celsius, which is 296 Kelvin. So just add 273. So when I plug those in, I get my mole value of 0.0279 moles about. So that's the answer to question 1. And then it says determine the molar mass. Well, the molar mass is mass divided by moles. I've got the moles now. What's the mass? Well, the mass comes from these bits of data. In this type of lab, if you measure this canister of gas before and after you release the gas, then you'll know how many grams of gas went into the sample of gas. So that's what the data is telling us here. We're looking at the change in mass. And so if we subtract those two, the change in mass is 1.219 grams. And we've determined from the other data that the moles is 0.029 moles. And when I divide those two, I get the molar mass, which is 43.7 grams per mole. So you can do it in 2 steps. You use the gas law to get you the number of moles, and then you use the mass with those moles to get the molar mass. Or we also could have plugged everything in to this equation right here, and we would have gotten the molar mass in 1 step.